So now finally we'll look at more general non-dimensionalization. And this we do by saying instead of having just a length scale and a velocity scale, we can also have a frequency in the as a time parameter. So now instead of the earlier rescaling of the time, we now say t dash is t times omega. So for example, if you have d by dt, that gives you 1 over omega. D by dt dash gives you 1 over omega d by dt. So this is a forcing at a frequency omega. And that could be, omega could be u over L. Velocity over the size of the length scale. And so basically the case that we looked up in the previous video is a special case of where we pick a particular frequency. And then if we want to include gravity as well, then we'll say, hey, gi dash is gi divided by our standard gravity. So let's do the same rescaling as earlier. So same for u and x, but now with t and g difference here, and same p. And then our new equation looks as follows. So now we have 3 non-dimensional parameters here. The earlier one is still retained, that's here, and this is 1 over the Reynolds number. This number here is called the Froude number, abbreviated as FR. And this here is the so-called Struhal number, abbreviated as ST. So in terms of interpretation, Struhal really is the ratio of the unsteady acceleration term versus the advective term. So that really is basically gives you an insight of how those two relate. And the Struhal number, for example, tells you how many vortices, how quickly you're shedding vortices behind an airfoil, for example. So if we look at these two terms, they are proportional to du dt, that's the top one, over u, and this really is, du dx in the simplest way. So it scales as omega u over u squared L, which is just omega L over u. So non-dimensional parameter, and when omega is u over L, as we had it in this case up here, then this term actually, the Struhal number, goes to 1. And then you're only left with the other, with the Froude and the Reynolds number. Now the Froude number basically tells you how important the inertial term is. So the inertial force versus the external force. In our case, mostly gravity. And and it's really the square root of that, actually. So if I do the same scaling here, we have rho u du dx divided by rho g to the power of a half. And you can show that this is u over the square root of gl. And so this here really up here is the Froude number squared. And in many applications, the external force is small, so we are often in the large Froude number limit. So then I can write my equation as St and this is my complete non-dimensional Navier-Stokes equation. And so if, as long as St, as Struhal, Froude and Reynolds number are unchanged, the dynamic form of our solutions remains unchanged. But you can change the values of rho, g, mu, or the geometry like L or the velocity u, but you don't change the dynamic form of the solutions. And people use that all the time. If you want to, model some large-scale ocean flow, you can, if you have the right dynamic similarity, the same, as long as you keep the Reynolds number the same, you can have the same flow in a small lab tank as in the ocean, and it will have the same dynamic behavior.